Hello students, this is Sashikil and today we are going to discuss AQA 9630 physics, and the topic today is scalars and vectors, and this is our lecture number 2 for that. In the first lecture we have discussed the nature of scalars and vectors, and we looked upon some examples, you know, like velocity is vector, speed is scalar, mass is scalar, force is vector, acceleration is vector, displacement is vector, while distance is scalar. Next, we already discussed addition of factors by calculation or scale drawing. So if you want to take a review of this, then you have to look for the vectors video part 1. The link for that is shared in the description of this video. Today, we are aiming to look at the conditions of equilibrium for two or three coplanar forces acting at a point. And along with that, we will be looking upon appreciation that objects which are in equilibrium, they can be at rest or moving at constant velocity. So this is our objective today, and the significance of this video is that vectors are the integral part of AQA A-levels, CAIE A-levels, IBDP, and Edexcel A-levels. So in this video, we will be focusing upon the topic understanding and solution to some tricky vector problems. So let's start with equilibrium. Well, this is a very common everyday life word. Equilibrium, balanced state. So if we look upon equilibrium, we can say that any object can be in equilibrium if it is satisfying two conditions. The first one is, of course, the resultant force. The resultant force or the net force acting on object should be zero, while the second condition is the sum of the moments acting on object or the net moment acting on object should be zero. So these two are the essential ingredients for an object to be in equilibrium or in balanced state. And remember, balanced state means that object can be at rest. It is said to be in static equilibrium, and it can be moving with uniform velocity or in uniform motion. That is said to be in dynamic equilibrium. Well, interestingly, there are two more ways in which we can state the equilibrium, the more detailed ways now. The first one is if the object is in equilibrium, then the horizontal and vertical components of the forces acting on that object should be zero. Then we say that the object is in equilibrium. So this is the condition from resolution of vectors, like you resolve the vectors acting on object, and if all the horizontal components are equal to each other and vertical components are equal, so we can say that the net force acting on that object is zero. And of course, if the forces are point forces, then the net moment is also zero. The next condition is when all the forces acting on object are drawn to scale, like if you are trying to draw the diagram, the triangle of the forces, and if you get a closed triangle, then we say that object is in equilibrium. And remember, what is this closed triangle? It is actually the cyclic triangle, in which all the vectors are arranged in head to tail rule. Okay, the next thing is I'm going to tell you some example for three coplanar forces which are acting on an object, and we have to show that the object is in equilibrium. Well, the three forces, one of them is 4 Newton, the other one is 3 Newton, and then the last one is 5 Newton. And these forces are acting at one point. So you know that when the forces act at one point, then the net moment is zero. So these are point forces. Point forces means that all the forces are acting at one point. So we conclude that the net moment produced by these forces is already zero. So it means that our second condition of equilibrium is already satisfied. Well, if we want to satisfy the first condition, and that is that the sum of the forces or the resultant force acting on that object should be zero, so we have two ways to do that. The first way is that you make a triangle, and that triangle will be a cyclic triangle. So if it would be a cyclic triangle, then we can say that the object is in equilibrium. Or the second way is that you find the resultant of F1 and F2, and that will be equal to F3. So we say that the net force is equal to zero. So the easier way is finding the resultant. So you know that uh, let me draw it over here. If I'm using the triangle method, this is 4 Newton, and then according to head to tail rule, this F2 is being plotted over here, which is 3 Newton, and they are aligned at 90-degree angle. So now we draw the resultant of these forces. So let's say the resultant comes out to be this. So you use Pythagoras theorem to find the resultant. So using Pythagoras theorem, you got the resultant, and that resultant is equivalent to 3 square plus 4 square and then the square root. So solving it up, you get an answer of 5 Newton. So it means that we can say that resultant of these two forces is equal to 5 Newton. So this 5 Newton and this 5 Newton, as it is in opposite direction, so they will cancel out each other. So we say that the net force acting on this object is zero. So that's how we can say that by solving it, we can say that these are in equilibrium. The second way is just drawing a cyclic triangle, because if you can draw the cyclic triangle, then we can prove that the object is in equilibrium. So let's try to draw the cyclic triangle. So the first vector that we can draw is this 4 Newton. And the second vector that we can draw is, you can say this F3, which is 5 Newton. So just draw this F3, which is 5 Newton. And lastly, the 3 Newton force would be drawn over there. So you can see that I have not changed the direction of any of the force, but I have just changed their position. 3 Newton is upward, 5 Newton is downward at slant angle, and 4 Newton is to your right. So this is called a cyclic triangle. Why? Because all the vectors are pointing in same direction, head to tail rule. So we say that we simply conclude that the resultant force acting on it is zero. So in this diagram, we have proved that the two conditions are fulfilled. Firstly, the forces are point forces, so no net moment. And secondly, the cyclic triangle, or through the vector triangle method, we proved that the resultant force is zero. So here you go. This is the way to prove it. Nextly, there's a very important concept, which is the inclined plane. Let's suppose this is a surface, or you can say a plank almost over there. So this is an object which is placed on it. And if we label the forces on it, we can say that the weight is acting in downward direction and normal reaction force is acting in upward direction. So these two forces are equal to each other. So that's why we say that the resultant force acting on it is zero. That's why this is at rest. So it is in static equilibrium. Know about the inclined plane. This is the inclined plane. Inclined with angle of inclination of theta, and let's say the object is placed on it. Now, again, labeling all the forces on it, the weight acts vertically downward and the normal force is perpendicular to the contact surface. And what we will do is we will try to resolve uh, this weight because the weight is at some angle with this slope. So if you want to resolve it, the component adjacent to angle is always cos. So this is W cos theta. And the other component which is perpendicular to this cos one, this is sine theta. So this is W sine theta. So now we can say here there is another force which is acting on this object, and that force is the frictional force which is acting here in upward direction as the sliding direction is downwards. So that's why the frictional force is upward. So this is the possible sliding direction. It is not sliding yet, but if it slide, it comes down. So over here, we can say one thing, that this object placed on inclined plane is in equilibrium. How it is in equilibrium? Because we have resolved W. So resolving W and then looking at the components, if you remember, I told you earlier that the object is in equilibrium if the horizontal component of forces are equal to each other and the vertical components are equal as well. So we can say that the object is in equilibrium. So over here, we can see that in this case, this support force or the normal reaction force is equal to W cos theta. So what we can do is we can simply write the expression over here, which is support force is equal to W cos theta. And next, what we can do is we can say that this W sine theta is equal to friction if the object is not sliding downward. So it means that we can easily say that the friction upward the slope is equal to component of weight down the slope. So as these are equal, so we say that this object on the inclined surface is in equilibrium. So these are the vertical components of the forces, and these are, let's say, the horizontal component. Like not perfectly horizontal, but you can say it's as they are acting along the plank, so we can say they are the horizontal components. Okay, moving forward to a new situation, you can see that a box is over there and its weight is acting in downward direction. So the weight acts vertically downwards, and then the support force is S. Well, the angle of weight with the line of action of support force is theta, that is equal to the angle of inclination, and the support force is always perpendicular to the contact surface. There is another force, which is friction, which is preventing the downward slide of this box. So if we just look upon it, so what we do is we will be resolving this weight with the theta. So this is W cos theta, and then the other component which will be acting down the slope would be W sine theta. This is similar to the case as we have done before. So what we can write over here is we can say that the support force here would be equal to W cos theta, and then the upward force of friction is equal to downward component of weight, right? So these two are equal. So we can prove that when they are equal together, then the object is in static equilibrium. Well, one more thing, if we want to know some unknown quantity from here, we can find that as well. Let's say if they ask you to find S, the support force, how much is the support force? And they gave you the W and they give you this angle. So if both these things are given, what you'll be doing is you will be simply putting the values over there, like the value of the W over there, the value of the theta over there, and you will be simplifying that to get the value of this support force. And similarly, you can put these values over there to get the value of the friction involved here. Okay, looking on another thing, which is testing three forces in equilibrium. So you can look at the example. This is a setup of three weights, W1, W2, and W3. So these three weights are hanged with the help of some pulleys. And then let's say these are the pulleys. So this is first pulley, and this is the second pulley. Pulley is just a wheel on which a slot is there through which the string is passing, and we can make the movement of the object. So this is weight W3. Okay, you can look here that there are three forces, like W3 is acting downward, which is F3, W2, and W1. So in fact, this F1 is the force of tension in this rope, and this F2 is the force of tension in the other rope. And this force of tension is actually because of the weights attached over there. Similarly, the F2 force of tension is equal to the weight W2. So in this type of questions, usually we have been asked to show that the object, the whole system is in equilibrium, or you have to find any force or any angle over there, right? So these are the angles theta 1 and theta 2, which these ropes are making with F3. And one more thing, these can also be given like this. So this is, let's say, theta 1, and this is theta 2. So theta 1 and theta 2 are the angles that the tension T1 and T2 are making with the vertical axis, the axis that is passing through W3. So if we look here, we have made the vector diagram for that, and then we complete that to form a parallelogram, right? So once we draw the parallelogram, so you know the resultant is always from the diagonal. So this is the resultant, and that resultant is always equal to F3. So we say that resultant of this is equal to F3. So using this, we can find the weight W3. Okay, so now let's look upon this thoroughly for this same question. There is some more explanation. Here is an object, the same object, let's say W, which is hanged with the two ropes. And both the ropes are having tension T1 and T2, and T1 is making angle of theta 1 with a vertical line, and T2 is making an angle of theta 2 with the same vertical line. And this is the vertical line, which is also the line of action of this weight. So what they say is that the object W of weight W is supported by the vertical string, which is supported by two strings at an angle of theta 1 and theta 2 to the vertical. And then you have to suppose that the tension in the first rope is T1 and the second rope is T2. And then at point P, where the string are being joined, the forces T1, T2, and W are in equilibrium. So you have to show that. So there are two ways. Of course, the first way is you can make a triangle of that if you want to show that this system is in equilibrium. So the first method is draw a triangle. Draw a closed triangle. So this is the first way to do that. And the second way to do that is vector resolution. So you just resolve the vectors, and let's say you have to resolve T1 and T2, and then vertical and horizontal components will be equal together. So let's do the first one. If you resolve the vectors T1 and T2, you can see that T1 sine theta will be equal to T2 sine theta, and that will be the horizontal component. Let me do that for you. So let's say if you're going to resolve T1, so this component of T1 adjacent to the angle is what? Yeah, you're right. It is cos. So this is cos theta 1. And similarly for T2, you yeah, you're absolutely right. It is T2 cos theta 2. So these are the vertical components here because they are in vertical direction. And now if we look upon the other option, so the other component here is T1 sine theta 1, and for T2 it is T2 sine theta 2. So based on this, what we can do is just make a square, make a plus sign like that, and then you represent all the forces acting on it. So this is T sine theta 2, this is T1 sine theta 1, and here are the two forces, T1 cos theta 1 and T2 cos theta 2, and downward is the weight. So if the object is in equilibrium, so we can say that the vertical components are equal together and the horizontal components are equal together as well. So that is written over there, that T1 sine theta 1 is equal to T2 sine theta 2. So this is the first thing that is shown over there. Now the second thing is, if you look here and you resolve it vertically, so you can see the vertical are T1 cos theta 1 and T2 cos theta 2. Okay, so T1 cos theta 2 plus T2 cos theta 2, these are equal to W. So that's why we can say that this object is in equilibrium. If you want to show it in another way, that is the triangle way. So how you will do that? That is again quite simple. You make weight W, and then you draw T2 over there, and then you draw T1 over there. So you can see that this is a cyclic triangle because all the vectors are arranged in head to tail rule. So when it is cyclic, no need to draw and do any calculation. You can just say that as it is cyclic, so the net force acting on it is 0. Moving forward to a famous question of uh, an archer pulling the bow, and let's say at the moment he's holding the arrow over here, and then of course there should be the tension in these ropes, right? So the tension is over there, and the angle that the rope makes with the arrow is 70 degree, and the force needed to hold the string at this position is 95. So this is 95 Newton, which is the pulling force. So you need to show that how much is the tension in each part of the string. And as he's holding it, so it means that this whole system is in equilibrium because it is at rest. The arrow is not moving. So if you want to find T, what you will be doing is you will be resolving T. So you'll be resolving both t's. So when you resolve the first t here, it will be t cos 70. And if you resolve the other t here, it will be same t cos 70. And then as it is, the other component here will be t sine 70, and the downward will be t sine 70 as well. So as it is in equilibrium, so we can say that T sine 70, the upward force, is equal to the downward force. So this is cancelled away. So there is no vertical component over there. If you look at the horizontal component, the 95 is acting towards left, and then 2t cos 70 is acting towards right. Okay, so what we do is we can find the value of t from here, which is 95 over 2 cos 70, and this will tell you the answer. Similarly, the resultant force on arrow at the instant of the bowstring is released from the position. The resultant force on the arrow. So that is actually the same force, which is 2t sine theta. So resultant force is 2t cos theta, sorry, cos 70. So you just got the value of t. So put that value over there, the value of t, and that will tell you the value of the resultant force. The next one is again, a camera is held by the two ropes, and you need to show that the tension is approximately 400 Newton. The tension in Y is approximately 400 Newton. So you have to show this. Okay, so the tension in X is already already shown, which is 450 Newton, and then the weight of the camera is not given over there. Yeah, it's not given over there, but it is stationary. Okay, so what we do is we actually resolve. So whenever you have to resolve, what you do is make a plus sign over there, and then you just resolve these forces. So x and y. So when you resolve x, so you can say that as this is 32, so you can say that this one is 450 cos 32, and this one is y cos 14. And if you do the vertical components, this will be 450 sine 32, and the other one will be y sine 14, and the weight of the camera is still unknown. So as it is at rest, so the horizontal components are equal together, so you can do 450 cos 32 equal y cos 14. So from here, you can find the tension in y, that is 450 cos 32 over cos 14. So don't cancel the cos, but just take the value of cos 32 and cos 14, and doing this, you can find this ty. And similarly, you can find weight as well. So the weight is equal to 450 sine 32 plus tension in y sine 14. So as you get the tension in y answer from there, so just put it here to find the weight of the camera. Okay, so the next one is a diagram is hanged over there, and what you have to do is you can see the dimensions are given over there, and the angles are also given over there, and the weight is 24 Newton. Well, a nice picture is there. So this is 24 Newton. So what you have to do is you have to copy the diagram and mark the forces acting on the picture. So copying the diagram, well, I am not the artist, but let me just try to copy this diagram. Okay, so yeah, let me copy it. Oh my God. You have to tell me that whether my drawing is too bad, bad, worst, whatever you can say. Okay, so you have to make the forces. Okay, we know that. We are studying physics, so we know everything. So the tension is always towards the fixed end. This is the fixed end. So this is the tension. This is the tension. And weight of the whole picture is acting downward. So we're done with the first part. We level three forces. Calculate the tension in each section of the car. So you have to find the tension. So what I do is you can do vector resolution method, or you can use vector triangle method. VT is triangle and this is resolution. I have already tried vector resolution, so you can try this yourself. And let me try now vector triangle method. Okay, the W is acting downward. One T is this direction and the other T is in this direction. Like I have arranged all the forces according to head to tail rule. Okay, now the problem here would be the angle, because the angle over there is with the horizontal axis. So we have to see that how much angle of this tension is with the vertical axis. So you can see that the vertical is 90 with this. So if this is 25, so this is 90 minus 25. That lead us to uh, 65. Yeah. So it means that T's angle with the vertical line is 65. So the T angle with the vertical line is 65 degree, not 650. So this is also 65 degree, right? Okay. So now you can work out for this angle, which is 180 minus 65 plus 65. So which I hope comes out to be 50 degrees. So you know all three angles and you know the weight. So what you will be doing is you will be using the sine rule. So use sine rule here to get your answer. And you know the sine rule, it is 24 over sine 50 is equal to t over sine 65. Doing this, you can find the value of t. Well, the wall climbing example, if this person is climbing the wall and this is the vertical axis, the tension is that way, and this is the angle theta, the weight of the person is acting downward, and then there must be a force which is acting from the point of contact that will be the normal reaction force over there. So we can do it like weight is acting downward, the normal reaction force is that way, and the tension is acting this way, and this is angle theta. Why the R is acting that way? Because it has to be point forces. Why? Because the object is in equilibrium. So all the three forces must be having the same point of intersection. T, W, and R must be passing through the same point. Okay, you can solve this problem. I'll be sharing the answer in the description so you can check that whether you have done it right or wrong. So over here, the tension is that way. The weight of this person is acting downward. And of course, the tension force again would be acting that way because it has, sorry, the reaction force because it has to pass through this because these must be the point forces. So again, it will be the same. The weight of the person is 390, and then the angle of this phi is 25 degree, and this angle is 40 degree. So you can just make the triangle, weight, and then this R, and then this T, and this angle is 25 degree, this angle is 40 degree, and the weight of the person is 390. So of course, using sine rule, you can find out the tension in this string. The next question, you have to find the vertical component of the normal reaction force. It's exactly the same question that we have done before. So try to make a vector triangle yourself, vector triangle, and then try to look for the vertical component of FR. This the vertical component of FR, not the FR. I'll be including the answer in the description for these questions. Okay, this is the next question, which you will try to solve yourself, and I will be adding the answers in the description. And same is with this. Uh, you will be solving it. Again, whatever you have to solve, you have two methods. The first method is vector resolution method. Vector resolution. And the second method is vector triangle method, right? So try to do that. I will be adding the solved solution of these in the description. So you can comment in the end of the video if you want further description for these questions. Thank you so much. I hope that you have liked the video. If you have liked the video and you got some knowledge as well about the vectors, so do put a like on the video, and if you're not subscribed, then do subscribe to my channel as well because I am aiming to make the complete video lecture for AQA A-level physics along with the solution of the complicated problems as well. Take care until